Let's practice a little bit more on resonance and formal charge in determining the best Lewis structure. So phosphate, we know, has 5 valence electrons in phosphorus, plus 4 of the 6 valence electrons in oxygen, and then 3 extra electrons. So for phosphate, I have a total of 4 times 6 is 24, plus 5 plus 3 is 32 electrons. Now, there's very, very many different methods to draw Lewis structures. It's really what method works for you the best and what makes the most sense to you. Now, what has always clicked in my head, which isn't not the only way to do it, is to have every single structure written out with the number of valence electrons around it. So first, again, we calculated how many overall valence electrons there are. And then what I like to do is kind of just put my central atom in the middle and the exterior atoms around it. Now, phosphorus can make how many bonds? So if I have a little cheat sheet here on the side, I know phosphorus is in group 5. It has 5 valence electrons. And oxygen is in group 6. Each oxygen has 6. So you can see here that I can bond 3 times to my phosphorus and only twice to my oxygen. So phosphorus is my central. So then I place my phosphorus in the middle and my 4 oxygens around. Now, something that I personally like to do, instead of bonding them together, I like to write out all of the valence electrons that I know I have for each of my atoms. So I know phosphorus has 5. 1, 2, 3, 4, 5. And each oxygen has 6. So I place each of my electrons around. Alrighty, now I've used my 5 valence electrons for my phosphorus and then the 6 valence electrons for my 4 oxygens. What I have not used yet are my 3 extra electrons. Now I have to use those as well. Now something I want to point out is your extra electrons are obviously not going to go to the phosphorus, because if I place 3 electrons here, my phosphorus is going to be happy and then it wouldn't bond to my oxygens. So I actually wouldn't bond them to the phosphorus. But other than just knowledge of that, there is another reason. Between phosphorus and oxygen, which one is the most electronegative element? Well, oxygen is further to the right on the periodic table. It is more electronegative than phosphorus. Therefore, what does that mean? Oxygen wants to have more electrons than phosphorus. So when there's gaining of electrons, oxygen will gain the electrons over phosphorus. So it doesn't matter which oxygens you give these electrons to, but what I would do is get the 3 electrons in your structure, because then you have all your 32. Now, it wouldn't make sense to use all 3 for 1, because for 1, then you have 9 and you don't want that. And 2, they're not all going to go to one structure because they have to still bond to the phosphorus. So again, it doesn't matter where you place them, but I'm going to place one here, here, and here. All right, now I'm going to change my color and I'm going to bond, because now I have my central atom, my other atoms around, and I've placed all of my extra atoms that I needed for this ion. So then I say, okay, well, I know that this electron and this electron can make a bond. This electron and this electron can make a bond. This electron and this one, and then this one and this one. Awesome. Now, I still see a problem. So I have 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. All these 3 oxygens, so you know what I'm talking about, these are all satisfied. How about that oxygen on the bottom? Is that satisfied? 2, 4, 6, 7. So I don't have this oxygen satisfied. Also, my phosphorus has 2, 4, 6, 8, but then it has this one lonely electron here. So they have to bond. So what that means is there's going to be a bond between that electron and that electron from the oxygen. So if I clean this up, it'll look like this. Oops. Now let's double check. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Great, so I still have my 32 electrons. Now, am I satisfying the octet? Each oxygen has the octet satisfied, but what about my phosphorus? 2, 4, 6, 8, 10. The phosphorus does not satisfy my octet rule. Now, we learned that when you want to satisfy the octet, you can push the electrons from a bond into a lone pair to get the following structure. Two, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Great, I still have my 32 electrons, and now every single element has an octet. Super important is to make sure that you have your brackets and your 3 minus. But now, how do I figure out which one's the better structure? Now, if you can't expand the octet, then you would have to go with the bottom structure here. But phosphorus is in period 3 on the periodic table. When you are in period 3, you have a 2, 1, 0. You have d orbital, p orbital, and s orbital. The d orbital is 5 orbitals. I can have 10 electrons, plus the 6 from the p, plus the 2 from the s. So I have space for 18 electrons. So what that means is I can expand my octet. The way that I choose which structure to go with is through formal charge. So let's calculate the formal charge for both of these structures. Formal charge of phosphorus will be number of valence electrons. My phosphorus has 5 valence electrons, minus my number of non-bonding electrons. There's no electrons around the phosphorus, so that's 0. Plus the number of bonding electrons divided by 2, or multiplied by 1/2. 2, 4, 6, 8, 10. Since I have 5 bonds, that's 10 over 2, which is 5, minus 5 is 0. Then I look at my oxygens. Now, these are all my oxygen 1 because they have the exact same formation. This 1 bond and then all the rest are lone pairs. For my oxygen 1, my number of valence electron is 6, minus non-bonding electrons are also 6, plus since I have 1 bond, there's 2 electrons in it, 2 divided by 2. 2 divided by 2 is 1, plus 6 is 7. 6 minus 7 is -1. So each of my oxygens here have a -1 charge. -1, -1, -1. My phosphorus is 0. Now, what about my formal charge for my other oxygen? I'm going to call that my oxygen 2. 6 valence electrons minus, I have 4 electrons that are not bonded, plus I have 2 bonds, so that's 4 electrons in the bonds divided by 2. 4 divided by 2 is 2, plus 4 is 6, minus 6 is 0. Now, a way to check that you've done the right charge is when you calculate up all your formal charges, if you have a neutral molecule, they have to be 0. If you have an ion, they have to equal the charge. Since we have 3 minus 1s, that's -3, and the rest are 0, that part of the charge in the formal charge in the structure is correct. Now I'm going to do the same exact thing for my structure on the bottom to be able to figure out which one is the better structure. Review. The goal is to have the least amount of formal charge because that is the most stable element. Remember that no compound wants to bond to anything else. So if there's more of a charge difference going on for one compared to the other, the one with the least amount of charge, the more zeros you could say, will be the most stable. So formal charge of my phosphorus is 5 minus, I have 0 non-bonding plus 1, 2, 3, 4, 4 bonds. So that's 8 electrons divided by 2. 8 divided by 2 is 4. 5 minus 4 is positive 1. Now, each of the oxygens is going to be the same this time. They all only have one singular bond. So for my oxygens, I have 6 valence electrons, 6 non-bonding plus one of the bonds, so that's 2 electrons divided by 2, negative 1. So plus 1, negative 1 for each oxygen. Now, plus 1, negative 1 is 0. With the other 3 gives me my negative 3 charge. So this structure is also drawn correctly. Now, which one is the better structure? The top one. Why? Because even though I have an expanded octet, which I'm allowed to have since phosphorus exceeds with the d orbitals, it's in period 3 or below, I have the least amount of formal charge. So this is my best, or better, I should say, structure. Now, you'd think you're done, but you're not done. Now, the one last thing you would have to do in a question like this is, well, my double bond is down on this oxygen. Is that my only possibility? And the answer to that is no. You have 3 other possibilities. So you have resonance. Now, resonance occurs when you have a structure like this and you can move around the bond. This is my original structure. I've already determined that with the singular double bond, it's the most stable. Then my other resonance structure will have the double bond move to the other oxygen. Then to the other oxygen. And then to the other oxygen. The reason we have 4 possibilities is because there's 4 different oxygens where the double bond could be. Oops, that's wrong. Ah! Perfect. So that's reviewing a bunch of stuff. How to draw Lewis structures, how to figure out if you have the best structure through formal charge, and if you have resonance. So something I really want to stress here is you don't always have resonance. It's not very common. It happens when you have multiple bonds because you can push the bonds just like we did here, how we push the electrons from this bond. So if you do that, you could sometimes have resonance, but it's not always there. Let's do another example where the resonance is not as obvious. So let's do SCN. So first thing, how many total electrons do I have? Well, this is 6, this is 4, and this is 5. That comes out to be 15 electrons. Oh, I forgot there's a minus charge here, so I have a plus 1 as well. So 15 plus 1 electron is 16 electrons. Which one will go in the middle? Sulfur has 6 valence electrons. It's in group 6. Carbon is in group 4. And nitrogen is in group 5. So, do you see how carbon can make the most bonds? Well, that means carbon's going to go in the middle. So I take my carbon in the middle, and therefore my sulfur, whoops, where did I just go? There we go. Sulfur and nitrogen will go around. All right. Now, what I like to do, again, if you want, you can always start to make bonds. You know carbon wants to have 4 and then fill out the extra electrons. So let's do it that method first. Since carbon is my central atom, I know I have to satisfy it with the octet. Carbon doesn't have any lone pairs, so it has to make 4 bonds. Well, that would mean 2 bonds to one side and then 2 bonds to the other as one possibility. Well, that's 8 electrons. 16 minus 8 is 8 electrons, so I have 8 left. So that would mean 2 extras around each atom with the minus charge. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Each atom is satisfied with the octet. 2, 4, 6, 8, 10, 12, 14, 16. And I have my 16 electrons. Now, who's to say that the carbon would make all 4 bonds this way? I could have given carbon the bonds as a triple bond on one side and a single bond on the other, where then sulfur would have the extra electrons. 2, 4, 6, 8, 10, 12, 14, 16. So I also have my electrons here. Now I have one more possibility. What if sulfur had the triple bond from the carbon? 2, 4, 6, 8, 10, 12, 14, 16. So the reason that I show you this is because all of these are possible. Now this was just putting out the bonds. Let's do it the other way. Let's say carbon, nitrogen, sulfur. Sulfur has 6 valence electrons, right? Carbon has 4. Nitrogen has 5. Now I have this extra electron here that I have to give to a structure. Now between these, which one is the most electronegative element? Or the more electronegative element? In actuality, it's nitrogen. So let's give the extra electron to nitrogen. That would mean that I can bond here, and here, and here, and here, which gives me sulfur with 2 lone pairs, carbon, double bonded to the nitrogen with 2 lone pairs, which is exactly the structure that I had at the top. Now, nitrogen usually wants to have a triple bond, so that's where the resonance can come in, because you can push certain electrons in certain other ways and give different bond orientations to give different arrangements. Because what if we did this instead? What if instead of giving the extra electron to the nitrogen, I gave it to the sulfur? Then, well, I can bond right here. I can bond here, here, and then here to give me my sulfur with my single bond, the triple bond around the carbon with the nitrogen, and my minus charge. And then my last arrangement would come from the fact that I pushed one of the electrons to make another bond here, and therefore get the triple bond around the sulfur. Now, how do I choose which is my better structure? The way that I do that is through formal charge. So now we can calculate the formal charge. This structure here is the least likely. However, let's just test that by formal charge. So formal charge of sulfur is equal to 6 minus 4 non-bonding plus 4 over 2. That is 4 over 2 to that, 0. Then we have carbon, 4 minus 0 plus 8 over 2, and that's 0. And then we have nitrogen, 5 minus 4 plus 4 over 2, and that's equal to 4 over 2 is 2, that's negative 1. So we have 0, 0, negative 1. Now what about for this sulfur? For this sulfur, we have 6 minus 6 plus 2 over 2, that's negative 1. For this carbon, we have 4 minus 4 plus, non-bonding is 0. 8 over 2, and that's 0. And then for nitrogen, we have 5 minus 2 non-bonding minus plus 6 over 2, and that's 0. So negative 1, 0, 0. Then we look up here. Formal charge of sulfur, 6 minus 2 non-bonding plus 6 over 2 for bonding. 6 divided by 2 is 3, plus 2 is 5, positive 1. Formal charge for carbon, again, 4 valence electrons, 0 non-bonding, 8 electrons in the bonds, that's 0. Formal charge for nitrogen is 5 minus, just lost my train of thought, 6 plus 2 over 2, which is 2 over 2 is 1, plus 6 is 7, 5 minus 7 is negative 2. So I have positive 1, 0, negative 2. So this structure is still possible because I get a charge of -1. Now, which one is my better structure? Definitely not this because I have higher formal charge. Between these two, which one is my better structure? It occurs when the negative charge is on the more electronegative element. Which structure is that? The first one. Nitrogen is one of the most electronegative elements. It's more electronegative than sulfur, so the fact that the negative charge, meaning that we gave the electron to the nitrogen, was